Hello, welcome back to the channel where we are reviewing the principles and practices of commercial construction textbook. This video is dedicated to chapter 8, and that is all about reinforced concrete frame. So let's dive deeper into that. We've seen that concrete is the basic material in the construction of footings, foundations, and bearing walls. It is also widely used for making the structural frames of large buildings. And we saw columns, the girders, and the beams. And because these members are subjected to tensile stresses and concrete is weak in resistant tension, steel is added to the member. And then we are getting the term reinforced concrete. A reinforced concrete building frame may be erected by either of two methods. So they may be cast in place, and we already have seen that how that works in the previous chapters, or it can be precast members. So let's dive a little deeper into the principles of reinforced concrete. So to overcome the lack of tensile strength, steel reinforcing is added to the concrete to provide the necessary tensile strength. Steel has good tensile strength. It is ductile and can be rolled into rods, which makes it an ideal material for use as reinforcement. And please, as always, refer back to the textbook where you can see the diagrams, you can see tension stresses in beams, and you can see that under load, there's a tension failure in plain concrete beam. And when there is a reinforced concrete beam, it actually prevents tension failure. So codes provide the necessary guidelines for the proper placement and distribution of the steel, while engineers establish the amount of steel required within the section by calculating the loads that must be supported. So it takes relatively small amounts of steel to reinforce a concrete section, and many variations in section size and shapes are easily attained. So let's take a look at the reinforced concrete frame. So the frame consists of columns that support beams, which in turn supports the slabs. In many instances, the beams can be eliminated and the slab supported directly by the columns. Please refer to the images. You can see the structural steel cross bracing that provides lateral stability for precast concrete structure, how that is done in the field. So please always refer back to the textbook because it's important to see those images, not just hear about that. So reinforcing steel. The reinforcing bars or rebars are available in various sizes and grades. The grade designates the yield strength of the material used in the manufacture of the bars. The three most common grades are 40, 50, and 60. For example, a grade 40 bar has a minimum yield strength of 40,000 psi. Higher grades are available but are subject to a premium. So also please refer to the chart. There is a nice chart showing the reinforcing bar properties. So the size of a bar is designated by a number that represents the number of eighths in an eighth of an inch that make up the bar diameter. So a number 4 bar has a diameter of 4 times 1/8 of an inch. So that is a half inch. In Canada and other countries, metric bar sizes have been adopted using a similar approach for bar designation. And you can see how that actually works. So the number of the bar approximates the bar diameter in millimeters. And please refer to the chart. This is important to understand how that works. So we are moving to the next subchapter, and that's welded wire reinforcing. So that's another form of concrete reinforcing, and that consists of wire or round rod, either smooth or deformed, welded into grids. So commonly it's known as welded wire mesh or welded wire fabric because the spacing between wires is relatively small. So, and again, please refer to the calculations, how that is actually done. And you can see it for the metric system as well. So when you space the rebars, two important criteria must be considered in the location of rebars in a concrete section. The first one is sufficient cover must be provided to protect the rebar from the environment. And the second important thing is proper spacing must be provided between the bars to ensure that the concrete flows around the bars and develops the necessary bond with the bars. So the American Concrete Institute, in its building code requirements for structural concrete, that's ACI 318, lists its clear cover requirements for standard bar sizes in non-corrosive environments. And you can see all the requirements here. So minimum cover is also dependent on the maximum aggregate size used in the concrete mix. So it should be 1.5 times the maximum aggregate size for exposed condition and times 1 the maximum aggregate size for non-exposed conditions. The spacing of the bars depends primarily on the maximum size of the aggregates in the concrete mix and on the size of the reinforcing bars in questions. So again, refer to the sections here. It's important to understand. Reinforcing bar details. So rebars are cut and bent to the required shapes based on the requirements shown in the structural drawings. So typical details have been developed by the various interested parties within the industry. For example, the American Concrete Institute provides standards for typical details for bending of reinforcing bars. And the Concrete Reinforcing Steel Institute, or CRSI, provides similar details and requirements. So please be aware of that and refer back to the images. You can see the standard hooks for reinforcement, as well as some mechanical sleeves splices for large column reinforcing steel. So, and this is where we are actually moving to the next subsection. That's the splicing of reinforcing steel. Just because reinforcing bars can be fabricated and shipped only in predetermined manageable length, there are times when splicing of the reinforcing steel is necessary to achieve continuity of the reinforcement within the structural members in the building frame. Three types of splices are available to the engineers for splicing of reinforcing steel, and they are as follows: welded splices, mechanical splices, and lap splices. So each method has its limitation, and one method should not be substituted for another without approval from the structural engineer of record. So for example, mechanical splices are used where butt type splices are needed because of space limitations. And a mechanical splice usually consists of some type of metal sleeve that is held securely in place by a wedge driven over the sleeve ends. So again, please refer back to the images and you can see how actually it's done in the field. I just wanted to mention that the lap splice is the most common type of splice, primarily because of its simplicity, especially for the smaller bar sizes. So please remember that information when you design for your reinforced concrete. We are moving to the cast in place reinforced concrete structural frame. And there are three basic considerations in the erection of a cast-in-place structural frame. The first one, the actual building and erecting of forms of the size, shape, and strength required. The next one is the proper placing of the steel rebar needed for reinforcement. And the third one is the consideration must be given to the support of the formwork and placed concrete through appropriate shoring until the concrete has gained sufficient strength to support itself. So the size and shape of the members to be formed are indicated on the building plans, whereas the size and amount of material necessary to make the form strong enough are based on the loads and pressures involved. The size, shape, and amount of steel required are also indicated on the plans in the forms of column, girder, and beam schedules. So please always take a look at the schedules. So column forms. Column forms are often subjected to much greater lateral pressure than wall forms because of their comparatively small cross-section and relatively high rates of placements. It is therefore necessary to provide tight joints and strong tie support. Windows are often built into one side of tall column forms to allow the placing of concrete in the bottom half of the form without having to drop it from the top. And you can see the graphic how heavier column form is actually constructed. So also take a look at the light column ties, how that works, and light column form. So it's graphically represented here, and you can see how it's done. And there are pictures showing the horizontal column form stiffeners and horizontal steel yokes and vertical form stiffeners on a column form. So that's quite interesting to see. Also, you can see the bend in a plywood column form, so that is typical as well. And we are moving to the chart, and you can see typical column schedule with the standard units and metric units. So the length of a column form is determined by subtracting the thickness of the bottom of the girder from that the column is to carry from the column height indicated on the plans or in the column schedule. So once the column forms are in place, they must be plumbed, braced and made ready to support the ends of the girder and beam forms that will be built to them. So yes, refer to the schedule because this is important to know, but you don't have to memorize it. You just need it for the reference. Column reinforcement. So the reinforcing steel in columns consist of two parts, the longitudinal bars that run the length of the columns and the lateral reinforcing that encloses the longitudinal steel. The type, number of bars, spacing of bars, and size of reinforcing to be used in each column will be indicated in column schedule on the structural drawings, along with column sizes and heights. A typical column schedule is here. You can take a look at that in the textbook, so you are familiar and you know what to look for in the construction documents. So we can also see the pictures of the spiral reinforcement here, and that is important to understand how that is done. And we are moving to the girder and beam forms. So columns, girders, and beams on each floor of a reinforced concrete frame structure are usually placed monolithically, which means that the form must frame into one another. It's also important to remember that some parts of these forms may be removed before others. So, for example, the beam and girder sides may be removed first, followed later by the column forms, and finally by the beam and girder bottoms. So it's necessary to construct the girder and beam forms so that each part can be removed without disturbing the remainder of the form. And you can see the concrete structural frame here and how that works, and girder bottom supported by T-posts. Also some examples of the scaffold and supports girder form, as well as the girder form at column, how that is exhibited here. So spandrel beam forms. Forms for spandrel beams. Those are deep beams for span openings in outer walls. They need to be carefully formed. Form alignment must be accurate to produce an attractive wall. Shore heads are often extended on the outside to accommodate the knee braces used to keep the forms in alignment. The extended shore head also frequently supports a catwalk for workers. And again, you can see those pictures here. As far as the beam reinforcement goes, it serves three purposes. The first one is to provide tensile strength to that part of the beam cross section that undergoes tension due to an applied load. Second, to add compression strength to the portion of the beam cross section that is in compression. And the third one is to provide additional shear strength to the beam cross section. So tension and compression bars may be straight or bent and are held in alignment by the vertical bars and also resist shear. So the whole assembly is supported on chairs set on the form bottom to ensure that the reinforcement is not moved during the concrete pour. The bars are held in position inside the formwork by securing them to the form ties. Also, the concentration of steel in the top of the beam above the column is then it is necessary to be considered. So the beam is designed to be continuous over the support, resulting in high tension stresses in the top portion of the beam. So although unreinforced concrete sections have some shear resistance, code requirements specify that a certain amount of shear reinforcing is required in all beams subjected to a certain level of shear. The vertical bars or stirrups in the beam resist a combination of shear and tension stresses known as diagonal tension. Note that the shear reinforcing bars are spaced quite closely at the beam and to counteract the high shear stresses that occur in this portion of the beam span. So please refer to the images. You can see the beam schedule, and that's both in standard units and metric units. We are moving to the next subsection of the chapter. There are like three of them left. So this one is precast concrete structural frames. Precast structural members are of three types. They may be normally reinforced, pre-stressed, pre-tensioned, or pre-stressed post-tension. And let's take a look at each of those. So reinforced precast members are normally designed according to common reinforced concrete practice. As a result of factory control, high-strength concrete is produced whether or not it is required, for it is actually more economical to design reinforced concrete for higher strength in the range of 5,000 psi or better. The members of a precast structural frame are often pre-stressed. That is, the tensile reinforcement has been placed under tension before the member is erected. Pretensioning is a technique in which the reinforcement is placed in the forms and stretched against fixed abutments. Concrete is then placed around the wires or cables. Pretension members are made several at a time in a long bed, and the major requirements are therefore simplicity and quantity. So post-tensioning involves first forming and casting the member with ducts through its length. After the concrete is cured, reinforcement cable is placed in the ducts um, and anchored at one end. It is stretched against the concrete by means of jacks, such as um, the one that you can see it here. There's like a hydraulic tensioning jack, and I'm sure you've seen those. And yes, please refer to the images because they show the whole procedure here. The tendons are gripped and tension is maintained by various potential gripping devices that fit into the end of the member. Post-tensioning is economical if the member is long or large. Both weight and cost may generally be reduced by post-tensioning units longer than 45 feet or having a weight over 7 tons. Post-tension may be applied to the individual sections before they're placed in the building frame, or as in the case of slabs, post-tension is applied after the concrete has been placed and set. In many structures, post-tension is used to add stability to the overall frame by providing a fixed connection between the beams and columns. And again, you can see here the graphical representation of post-tension cables in a cast-in-place concrete slab beam. So precast girder and beam shapes have become standardized to a considerable degree, but it's possible to produce a special shape if required. So one great advantage in the use of these precast members is the possibility of erecting long free spans. And take a look at the precast beam shapes. You can see the single T beam, double T, edge beam, inverted T beam, ledger beam, and L-shaped beam. So those are the most typical shapes, and they're used in different applications. So column erection. The first step in the erection of a precast structural frame is the preparation of the column footing. Because the columns must be mechanically attached to them, anchor bolts have to be set accurately into the footing. Each column foot has anchor plates cast into it so that the column can be bolted to the footing. Large columns require special steel pads such um, as those to transfer the column load to the foundation. And again, please see the images, how that works. So a knot is turned onto each anchor bolt before the column is set over them. After erection, the column is plumbed using guy wires if necessary, and the nuts are adjusted until column rests firmly over them. Top nuts are then put on and tightened to hold the column in position. And finally, the space between the top and the footing of the column is filled with grout, often made with metallic aggregate to provide even pressure over the entire area. So we are moving to the next subsection, that's column to base connections. So double nut system with a 2 to 2.5 inch space between the top of the foundation and the bottom of the base plate for non-shrink grout is used, and you can see there's the illustration here. At each column location, it's necessary that sufficient ties be placed in the top of the pier or wall to secure the anchor bolts. Also, when we talk about beam erection, Beams are raised into position by crane, or some type of temporary connection is usually provided until the permanent ones have been completed. So, um, angle iron clips bolted through holes in the columns restrain the girders until the final connections can be made. And connections may be either moment resisting or pin type. So, moment resistant connections prevent rotation between the column and the beam and contribute to the lateral stability of the frame. For moment connections to resist the tension force resulting from the force couple that is developed, some method to produce continuity at the connection is required. Welding, shear anchors, inserts, additional reinforcing bars, post-tensioning, or some combination of these can be used to provide this continuity. Care must be taken to provide temporary bracing during the erection of beams with these types of connections until the connections have been completed. Pin-type connections, on the other hand, are designed primarily for gravity loads, but are not expected to resist lateral loads as such. Connections of this nature usually consist of plates or angles embedded in the beam ends that bear on similar plates embedded in the supporting section. They're normally welded together to prevent the beam from slipping off its support. So, beam to column connections. There are a few different methods um, for connecting beams to columns. So, the beams are rectangular in cross section here in the picture, but it doesn't mean that there are other that there are no other types commonly used. So there are 7 variations of beam to column connections, and they are as follows. The first one, this is a welded connection that conceals a column without using a depth and beam. It is for a simple span condition, but it can be used as a moment connection by using non-shrink grout between the end of the beam and the column and by providing for transfer of tension at the top of the beam. The second one, this is a welded connection, again with a beam resting on a corbel projecting from the side of the column. It's also for a simple span condition, but can be converted into a moment connection. Elastomeric bearing pads are shown, but are optional. Number 3, this is called the depth end connection, and it's also welded. And its development to a moment connection requires grout at 2 interfaces, which is a difficult field procedure. Number 4, this welded connection is often used when it's required that it to be hidden for architectural reasons. An H-shaped section is shown projecting from the column, but other structural steel shapes may be used instead. Number 5, this is a dowel connection with bars projecting from the column into steel tubes cast into the beam. Tubes are later filled with grout. The connection can be made continuous by welding tension reinforcement as shown here in the picture. Please refer back to the textbook and see those connections. Number 6, this is a welded connection in which the tension bars are welded to small angles. In future extension of the column, if future extension of the column is required, anchor bolts can be set into the cast in place concrete between the beam ends. And the last one, the 7th, in this type of connection, a post-tension bar is tensioned after the non-shrink grout has been placed between the column and beam end. So when we erect additional stories, there are a few things that we need to remember, and there are 5 basic methods for splicing columns And they are as follows. Number one, the main column reinforcement is welded to the base plate. Pockets may be filled at the sides of the column or in the corners. Number two, this connection also uses as inserted plate between the angles. The angle recess is grouted after erection is complete. Number three, 4 small corner base plates are used here rather than a full size one under the angles. Number four, reinforcing bars projecting from the upper column extend into steel tubes cast into the lower one. Provisions for temporary bracing must be provided. In number five, the column is spliced through a continuous beam and reinforcement is required within the beam to transfer the load from column to column. So we are moving to the floor and roof slab erection. So slab to beam connections should take into consideration the transfer of horizontal forces from slab to beam if it is assumed that floor or roof is acting as a diaphragm. So there are 6 typical connections. Number one, a bond beam is provided under the slab ends. At the joint between the meeting ends and the slabs, at the ends of the slabs is fully grouted. Number two, hairpin anchors cast into the bond beam are embedded in the grout between slab ends to provide positive anchorage. Bars may be grouted into the keyways between adjacent slabs to tie the slabs together lengthwise and keep preventing roofing problems at the joint. Number three, the pocket in the wall must be sufficiently large to receive the extended stem of the single T slab without difficulty. Elastomeric bearings, pads may be used if that is required. Number four, double T slabs rest on a bond beam cast on a block wall. Precast fill-ins between the T stems may be used as forms for concrete between the slab ends. Number five, single or double T units used as wall panels may have corbels cast with them to support floor or roof slabs. Vertically slotted bolted connections may be used to tie the slabs to the load bearing with panels, or the welded connections shown may be used. And number six, connecting a slab to a parallel wall requires a connection that can accommodate vertical movements. Slotted angles with low friction washers permit this movement. So we are moving to the next subsection, and that is architectural precast concrete. So architectural precast concrete has been in use for over 50 years. Originally, precast structural units such as structural frame used wood or steel. More recently, advances in design, control, and manufacturing techniques have been made possible and economical the production of precast units that are themselves finished components of a building. There are two principal methods by which this type of unit is produced. So one is tilt-up construction, in which the units are cast on the job site and tilted up into position. And the other one is an independent factory type production geared to making a variety of precast products in which all the facilities and economies of a production line type of operation may be utilized. So let's take a look at the factory produced precast concrete units, and they include the following. Excuse me, the advantages include the following. Freedom of design. So there are so many styles and designs that are possible. when you use this precast concrete units. Then a high degree of quality control, then a wide variety of shapes, sizes, and configurations. And there is the possibility of including in the precast unit some or all of the services that are normally installed after erection. So this can result in considerable saving of time and labor following the erection. So definitely this is an advantage. Then the use of precast components makes possible the rapid closure of the building that allows for earlier access by the service trades. Then precast panels can be fabricated as sandwich units with insulation laminated between the inner and outer layers. So this provides an energy efficient wall section. Also, curtain wall panels are units that carry no loads except wind load. They are set into or hung from the structural frame to act as closure units and to provide for architectural effect desired. Load-bearing panels carry the loads of floor and roof, and for example, they can be designed in width to suit the standard width of floor and roof slabs that they support. Again, refer to the images. You can see that load-bearing wall panels, they can also support open web steel joists, and some of the elements can be made from post-tension precast segments. You can see that here. So let's talk about the precast street furniture. So that is another group of precast concrete projects. So that is the major item in that planning should be the concept that the cost of making the molds should be spread over as many units as possible. So the more units can be made in one mold, the less the unit cost will be. And this leads to the concept of a master mold from which a large number of units for one project may be made. Some of them perhaps with minor modifications in the original mold. And again, please take a look at the images here. You can see how total envelope mold and conventional mold is made here. Also, you can see precast panel shapes. So one is closed, then one is open, and then there is a combination of both. So the joints between precast concrete panels are an important part of the overall project and will have been designed taking into account the structural requirements, degree of water tightness required, appearance, and cost. They will usually be one or two basic types, one stage or two stage joints. So one stage joints are simply sealed against water penetration by the use of a sealant near the outer surface. Two stage joints have a sealant near the outer surface and an air seal that is usually close to the inner face of the panels. So one major advantage of architectural precast concrete panels lies in the great choice of surface finishes available with regard to both color and surface texture. So colors are varied by using white cement, color pigments, and colored aggregates. So, and again, please refer to the images. You can see the texture, you can see the colors, and the panel surface, how that is designed, and there is a great variety of those. And we are moving to the last portion of this chapter, the last subsection, and that is tilt up load bearing wall panels. So originally that was developed for economic reasons. Improvements in technique have made it possible to produce panels that are also architecturally pleasing. So load-bearing panels may be produced by this system and function in exactly the same way as architectural load-bearing members. There are three common types of panels used as load-bearing members. So panels intended to carry pre-stressed roof slabs are cast with a continuous ledger near their top edge for this purpose. Then panels that will support a steel beam roof frame are cast with weld plates in their top inner surface, whereas panels intended to support open web joists are cast with seated weld plates and shelf angles. So if there are two-story panels, they may have ties cast into their inner face and the first floor level to tie into a cast-in-place concrete floor. So um, let's take a look at what else is important here. So yes, panel edge forms must be bolted, pinned, weighted, or otherwise held down. If they have to have holes for rebars, they will usually be split to facilitate removal. And you can see all the sections and diagrams and all the images here, how that is done, how openings, cast and tiled up panels actually work. So the method of tilting up depends on whether the crane can operate on the floor slab or on whether the panel has been cast face up or face down. Lifting can be done by the use of inserts and bolts, or in some cases, by the use of the vacuum lifters. So and this actually wraps up our chapter 8. Thank you so much for watching. I will see you in chapter 9. Thank you.